Hello Honors Chemistry and welcome to Chapter 6, Section 6.5, using chemical formulas as conversion factors. So previously we talked about the concept of molar mass and Avogadro's number, right? And how between those two things, right, we get the relationship between mass and moles, and we get the relationship between moles and particles, right? Now we're going to talk about using the chemical formula. What relationships are embedded in a chemical formula, right? And we talked about this previously in chapter 5, right? Well, we mentioned it in how to read a formula, and then we sort of moved on to naming, right? Well, here we revisit that concept, right? Where when I see this formula, Na2O, I understand that means, let's use the proper words, 2 ions of sodium, right, are for every 1 ion of oxygen. Yes? Right? That's what that means. Or we could say that there are 2 ions of sodium for every 1 formula unit of Na2O, right? Or I could say that there is 1 ion of oxygen for every 1 formula unit of Na2O. Yes? Okay. And so those are some of the particle relationships that we can draw from that formula, right? Likewise, for this formula, I could say that it's ionic also, right? So 2 ions of aluminum for every 3 ions of SO4, right? We could also say that there are 2 ions of aluminum for every 1 ion of sulfur, right? And the list goes on, right? We could say that there are 12 ions of oxygen for every 2 ions of aluminum, right? And we could write a few more, okay? Now, thinking back to the way the word mole works, right? Whether we're talking about 1 dozen, right? Well, 1 dozen means 12, right? Like there's a meaning there, right? But whether I'm counting by the dozen or I'm counting by ones, right? I'm still counting the same thing and the relationship means the same, right? So if I said 2 ions of sodium to every 1 ion of oxygen, it's still true if I say 2 dozen sodium for every 1 dozen oxygen. Yes, does that make sense, right? For me to say, and let's be clear here, right? 2 ions of sodium to 1 ion of oxygen is the same ratio as saying 2 dozen ions of sodium for every 1 dozen ions of oxygen. Yes, does that make sense? Which is why to say 2 moles of Na for every 1 mole of O is the same relationship. It's just a different scale, yes? This is talking about the individual particle. This is talking about on the scale of moles, right? So I could also say 2 moles of sodium for every 1 mole of that, yes? Likewise over here, I could say 2 moles of aluminum for every 3 moles of sulfate, right? And so forth and so on, right? And what this gives us is this gives us a way to describe the relationships embedded in a chemical formula, either at the singular particle level, right? Or at the larger mole level, where moles are just a scaled up number of particles, yes? And so these relationships all serve as, ding, 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 conversion factors, right? Which allow us to relate the different components of a compound to either the whole compound or to each other, okay? Now, let's go ahead and read some problems and do them together and we're going to read them very carefully to make sure that we understand how these problems are worded differently than the problems we did in the previous section, right? So this says to determine the mass of oxygen, right? So here's our goal, in a 5.8 gram sample of sodium bicarbonate, and here's our given, right? So note that it's saying grams here and grams here, right? So clearly it can't be grams and grams of the same thing, right? And so if we're thoughtful, we're asking for grams of a part relative to the whole, yes? We're asking for grams of a part relative to the whole, and that's what all of these are, yes? These are part versus whole relationships, yes? So, sodium bicarbonate, let's look at that formula, right? 8 means, right, polyatomic ion. Sodium is a metal, right, so definitely an ionic compound. So sodium has a charge of +1. Bicarbonate has a charge of -1. So NaHCO3 is our formula, and I would like to know the mass of oxygen. So let's go ahead and work this out. So 5.8 grams of NaHCO3. Now, I need a relationship between oxygen and sodium bicarbonate. So thinking back to what we just did, I know that for every one, let's use moles, right? So every 1 mole of sodium bicarbonate, oftentimes, if you don't know where else to go, moles are usually a good place, right? Are equal to oxygen, 3 moles of oxygen. Yes, that's a relationship that this formula gives us. So I can't use that until I get to moles, which means what do I need to convert to here? Right, I need to use the molar mass. So we have 84.01 grams of NaHCO3 for every 1 mole of NaHCO3. And then for every 1 mole of NaHCO3, there are 3 moles of oxygen, yes? And I know now if I want to get to grams of oxygen, I'm just going to use, right, the molar mass of oxygen. So 1 mole of oxygen is 6 grams of oxygen. And we'll see that my moles of oxygen cancel, moles of bicarbonate, grams of bicarbonate. I'm left with grams of oxygen. Yes? Make sense? All right. So, same thing. So, determine the mass of oxygen. Here's our goal. In a 7.20 gram sample of that. So, same principle. Let's go ahead and write our relationships, right? So, oxygen to aluminum sulfate. There are 3 sulfates, and there are 4 oxygens per sulfate, which means there are 12 moles of oxygen equal to every 1 mole of Al2SO4 okay? So then, 7.20 grams of Al2SO4 molar mass now. So we have 342.14 grams of Al2SO4 to every 1 mole of Al2SO4. And for every 1 mole of Al2SO4, going back to here, there are 12 moles of oxygen. And for every 1 mole of oxygen, I know that is 16 grams. And we'll see that all of our tidbits cancel. And we just need to do the math. Yes, does that make sense? All right. Thank you for listening. Be good. And in the next one, we move on to the concept of percents in chemical formulas. All right. Thanks for listening. Be good.